start recording now, and we're all very excited to hear Jack Morava talk about the rise of a braid as a TQFT. So over to you, Jack.
Thank you. Is my screen shared? Is everybody seeing a kind of an outline in type that's a little bit too small?
Yeah, it's quite small, but we can see it.
We can see it, yeah.
The rest of it looks like this, so that maybe that's irrelevant.
That's better.
I'll just, before I start, so this is joint with Dale, but before I start, Fred Cohen passed away a couple of days ago, and I wanted to just recognize that and say that he, this whole project starts from something that he did at the Prime 2, and he's kind of one of the fathers of the theory of homology of loop spaces of spheres and things like that, which are sort of the backbone of modern higher homotopy theory. May his name be a blessing, is what I wanted to say, I guess. I'll try to say some things about what he did as I go along. So let's see. Well, should I have gone through this thing? The first part is about braid groups. I guess the second part is roughly about mapping class groups of punctured surfaces, punctured spheres. And the last part is about sort of wide-eyed mysticism or something. You can skip that part. So I wanted, if please interrupt me and don't hesitate to ask for clarification. I wanted to say that I tend to confuse groups with categories that have one element with the groups as their automorphisms. It's kind of convenient if you take the geometric realization of that category, you get the classifying space of a group. And a good example, like it's, I think, not usually taught in undergraduate in early topology courses, but a beautiful example is that the space of finite subsets of the plane is a classifying space for the braid group. This goes back to Artin and Chow and people like that. So that's about groups. A group has one element, has one object. A groupoid is like a disjoint union of groups. And if you can take the disjoint union of the braid groups as a groupoid, you get a sort of some large groupoid whose classifying space can be identified with the space of finite subsets of the complex planes as following above. And that object is a topological monoid. This comes from the fact, so when you can take two braids and compose them by concatenation, or you can compose them by juxtaposition. And this gives you two operations on braids. And if you use one to make the first classifying space, you get a monoid, and if you classify that monoid and then take its loop space, you get a group-like space, an H space, which is the best approximation to the braid monoid itself by a CW space or something homotopy equivalent to it. It's a sort of, if you take this is the group completion construction, and it's very general. There's some further discussion of it later on. But classically, if you take an abelian group, take its classifying space, and then take its loop space, well, it doesn't have to be abelian. If you take a group, take its classifying space, take its loop space, you get something out of that which is homotopy equivalent to the original discrete group, if it was a discrete group. Whereas if you take a monoid still has a classifying space, and you take the loops on the monoid, you get something back in general different from the monoid. You get something back with a group action, with inverses. So you've, in some very universal sense, group completed your beginning monoid. And this is the growth and deconstruction for vector bundles. And it's sort of under control in things that are close to abelian in situations like vector spaces. When you take disjoint union, direct sum of vector spaces, that's a kind of commutative sum. But this theorem applies also to the non-commutative situation. And one of its consequences is that it's a homology isomorphism, or as much a homology isomorphism can be, given that you're made it into a group. It basically says that if you invert the elements in pi 0 on the classifying space of the group, then you get the group completion. It's enough to invert the stuff in pi 0. So for example,
excuse me.
Yeah.
Am I remembering correctly that for the plus construction, you need the commutator subgroup to be perfect or something like that?
For the classical plus construction, yes. But this is this is a sort of it's a blunter instrument.
Okay.
It's a sort of universal. It's a kind of existence theorem for this group completion. It makes sense in a lot of contexts, and its content is that it's very close to being a homology isomorphism, and it's essentially encapsulates what's often called stabilization, when you add more or more points at infinity or something like that. Is that, I mean,
yeah, you answered my question. Thank you.
Okay. What I'm saying here today is going to be mostly about this case, the case of the braid group, or the braid monoid. And it says that the braid monoid group completed is best approximated by an H space as the space of maps from the two sphere to the two sphere. So that space has many components indexed by the degree, whereas the braid groups, the original braid monoid only has 0, 1, 2, 3, whatever strands in its braids. So when you map the braid monoid to its group completion, in effect, you've inverted a braid and made this thing compatible with subtraction of braids. And you get this thing like what algebraic geometers call divisors, or something much like them on the sphere. That construction, can everybody see this page?
I see 2 pages.
Yeah, hang on. Oh no. No, not that. Here, can you all see this? This is in this talk will be concerned with things in dimension 2. I just want to remark, this is, for example, where Fred Cohen's work, his thesis, for example, came in. If you look at the configurations of n points, of k points in the n sphere, a finite subset of the n sphere, and think of them as the charged particles, then they have they define their potential energy is the gradient of their potential energy think of them as repulsive, the force as repulsive, they all have the same charge, gives you a map from the space of configurations to a space of maps from the one-point compactification of Euclidean space to itself. And it turns out that this that well-defined map instantiates, if you want to, the group completion theorem. That's the map that induces an isomorphism. That's a map that induces the isomorphism on homology given by the group completion theorem. It's tricky because that map, that potential, is normalized so that it takes 0 to infinity and infinity to 0. It goes back to Newton, but I think this particular version of it and its elaboration is due to Siegel and McDuff, Graham Siegel and Dusa McDuff. Okay, well, this whole talk is about writhe, the writhe of a braid, and its generalizations. And it started with me being confused about the configuration of a collection of distinct points in the plane, because such a configuration has this thing called a discriminant, where you take their differences as complex numbers and multiply them all together, which gives you a map from a configuration space to homotopically the circle. It never vanishes. And if you take pi1 of that, you get a map from the braid group to the integers, which for some reason I thought depended on the number of strands until Dale straightened me out about this thing. And the point is that this writhe, viewed this way, did I say that? That it's additive under both concatenation and juxtaposition. I'm sorry, I'm trying to, makes it be a kind of topological quantum field theory in the sense of Siegel and Atiyah and so on, thought of as maps from some interesting geometric category or category of topological objects that you can somehow combine, maybe by putting side by side or something like that. Looking at functors from them to more algebraic things like vector spaces, which you could maybe put side by side, or maybe you would take tensor product of. I've lost my images of where everybody is. Okay, I can't see you guys. Are there any questions?
Could you say a bit about what you mean by this n/z and
yeah, yes, thank you. I meant to, it's convenient to think, if you have a group acting on a space, it's convenient to think of its transformation groupoid, where the category has the space, elements of the space as its objects, and actions of the elements of the group that move these things around as the maps. That's a category. And this thing n/z, it's meant to be a collection of points indexed by the natural numbers, and each of those is thought of as having the integer z as its automorphism. So that would assign to a braid its number of strands and its writhe. That's a quantum field theory of some primitive sort. What this most of this talk is about has to do with the Burau representation, which is very classical and actually takes juxtapositions of braids into block diagonal sums of matrices. So it's monoidal is the first point of this. But I want to draw your attention to a kind of monster typo here, where it says pi1 instead of pi0. I just saw that this morning, and I'm sorry. I hope that won't confuse things. I think this pi1 down here is actually correct. So I want to describe, one way to describe the Burau representation is to say a collection of points on the sphere, back like when we were talking about electrically charged particles. So these would be points in the plane. And I want to think of these under the action of diffeomorphisms which fix the point at infinity. So they're sort of compactly supported. So there's one point at infinity that's left fixed, and then there's a finite subset of the plane indexed by these Z stars, which are left fixed as a set, but not pointwise. That's what this notation with a semicolon means. So pi1 of, so you take the plane, take this collection of punctures and pinch them all together to one point, and take pi1 of that, and you get a free group on K generators. So if you take the point at infinity and the origin, pinch them together, you get a torus with a collapsed cycle, which has pi1 equal to the integers. In general, you get something free on rank K, of rank K. And if you abelianize that, you get free abelian of rank K. And if you add those up, you get a map to the integers, a homomorphism to the integers, which defines an infinite cyclic cover, a kind of Alexander cover of this suitably punctured plane. It's useful to have this extra point out at infinity for if you want to work with pi1s. The first homology of that cover is free of rank K over the deck transformation group. Okay, I mean, this is the sort of the Alexander construction, which I learned at my granny's knee from Dale. I'm sorry. Is this okay? I need to remark that if you take two disjoint collections of points and put them side by side in Euclidean space, you have to sort of worry about overlapping them. You have to put some space in between. There's a kind of Boardman-Vogt technique of rigidification for these kind of things, these sort of little cubes and little squares constructions. Or in this case, you can sort of think of time zones where you have some points here in, Vladivostok and some other points here around Hawaii, and then some points here on the West Coast, that kind of thing. That keeps them from getting too scrambled. If you're working with braids and put them side by side, you get something that's strictly associative. But if you're working with configuration spaces, one dimension up, then you have to worry about these associativity coherences. But that's sort of standard tech machinery by now. So anyway, if you apply this construction, in the case of an Artin generator, you get this little nice matrix representation of, the Burau representation takes braids to automorphisms of this Burau matrix. And the automorphisms of the Burau matrix are elements of the general linear group of the group ring lambda, the sort of Alexander ring for this infinite cyclic cover that you this Burau construction, this Burau cover, I guess. Anyway, on a generator, it has this nice form, which you can think of as a deformation of a transposition. It has an invariant line corresponding to the determinant 1, which is inconvenient in some kind of calculations because it gives you an eigenvalue of 0 or something. And it's usually removed to define the to define the reduced Burau representation. But for our purposes, the Burau unreduced representation is the one that has the nice functorial behavior. In particular, the Burau representation is monoidal. It takes juxtaposition tensor product of braids to block diagonal sums of matrices. And that's monoidal, but it's not braided monoidal in the sense of Joyal and Street, which I'm sure everybody here knows more about than I do. Are there any questions? I'd like to be able to see everybody. Are you guys really there? Hello, hello, can you hear
If
me?
you go to
Yeah.
the upper,
I don't want to, lose the,
We're here.
We're all here. We're all here, Jack. Don't worry.
okay.
Jack, there's a little button at the upper right-hand corner of your screen, I think, that says View. And if you click on that, you may be able to see us all. You click
Yeah,
on
but
that.
but you'd have to stop sharing to do that.
Oh,
I'm just going to blunder on. But so
yeah.
this is all the more reason for you guys to object from time to time to keep me on track. Over here on this side of the page, there's kind of a description of the twist morphism in the Joel Street story, which is universe. It's a kind of universal braiding, and it's the obvious thing where you flop two big strands across each other, and if you write it out in detail, which I did or tried to here, it's to get it in the finite amount of space I had to write it as a product of products. You can at least count how many elements it has and how many ardent generators are required to do this, and it goes up, quadratically. It's very non-trivial. And if you take the Burau representation and see what what it gives you for the Joyal Street twist, you get some horrible thing. But because of the magic of determinants, its determinant is this nice little thing here, which looks very familiar. It's essentially the braiding you get for anti-commutative graded things in logical algebra, and it's where you just get to distinguish bosons from fermions in physics. That's at the value t equals 1 or minus 1 if you want anti-symmetric things. My sort of slogan for that is that the determinant of the Burau representation is the rive. That obscures the fact that there is this sort of parameter floating around in there, which is left undetermined. But this goes back to something which always bothered me, which was that the Alexander polynomial of a dot or link or a Conway version, it took till Conway for it to be uniquely normalized. And I think the first, I think it goes back to Vaughan Jones. Anyway, pinning down that exact formula for the Alexander polynomial of a knot in terms of the Burau representation seems to have a kind of square root of -1 lurking around in it. I think it was the best version of that. I mean, the first time it was ever really written down in detail was in Vaughan Jones, but maybe I'm wrong. Anyway, so there's another way to think of this determinant in terms of Picard groups of of modules, of graded modules. So this is where these things called anions, whatever they are, sort of begin to show up. If you look at one-dimensional projective, rank 1 projective modules over a reasonable commutative ring, they form a group under tensor product. They're called Picard. This is called the Picard group of the ring. It goes back to algebraic geometry, where they talk about complex holomorphic line bundles under tensor product as zeros and poles of rational functions. Anyway, these Picard groups are really sort of the homotopy groups of a Picard category, which has these projective lines as the objects under tensor product with isomorphisms, which are between them, which are given by elements of the unit group of the ring as the morphisms. So as a category, this has, basically it has the rank, so it has sort of, you can identify its components with Z corresponding to your line bundle, these are graded lines, so they live in some integral degree, and they have automorphisms, which are the pi1 of this Picard category, and which are given by the units of the ring. I guess what am I trying to say here? If you set things up this way, for the group, the determinant of the Burau representation lives in the multiplicative group of the ring lambda, and that group is consists of plus or minus 1 times an integral power of the generator, plus or minus 1 times Z roughly, which is what this this interpretation of the Rive in terms of line bundles is. So really, we're sort of thinking of the Burau representation as, so the Burau representation is an H1. It has rank K if you have K points or whatever. If you take its top exterior power, that's the determinant. Lambda in the exterior power sense of lambda in the Alexander sense is just is sort of rank is isomorphic to the integers, maybe plus times Z2, and that's the ride. But you're free to fiddle with this construction if you want to give the Picard group a twist by this Burau generator T. And if you do that, then let's see. Well, then you can see the writhe as the group completion of the writhe as a map, as I've got it written here, which is just goes back to that funny in double bracket Z notation earlier on. So
Jack,
yeah,
I have a question. Why is that a map of loop spaces?
Why
is
yeah, so
Picard group a loop space?
It's a the underlying, the Burau representation itself is a functor from some category of sets, subsets of the plane to some category of modules over lambda.
Mhm.
Okay, so sort of determinate module. So that's a functor from one big category to another, much still big, but much smaller category. And if you then take those categories and take their classifying spaces and group complete them, that because the original functor was monoidal, the group completion is going to be a morphism of group-like spaces.
So is there supposed to be a plus on that target, Picard lambda?
Oh, yes, thank you. That's another typo. Thank you. I'm sorry. Yeah, that's the point.
Okay, I get it now.
Yes, okay, thank you. Yeah, well, I think the Picard category, because it lives in only in dimensions 0 and 1, it's already it's already complete, because if you have a line bundle in degree 3, it has the inverse line bundle in degree -3. But it should have, the intention was to have a plus there. Thank you. And this just says that you can fiddle with this. And again, over here, this should also have a plus, if you can see where I'm pointing. And I should have given a reference to there's a literature of how you construct sophisticated classifying spaces for braided monoids and things like that, in such a way that a braided functor which commutes with braidings completes to a map of double loop spaces. That's a topic in higher category. I mean, a research topic. But it's, I think, pretty well understood. It's now they like 3 categories. So this is actually kind of an elementary factor, that I'm talking about the writhe and the discriminant and all. And there are other more sophisticated approaches to this kind of thing. And there's a very detailed paper of Jonathan Brundon, which impresses me and tells you how to make a kind of TQFT for framed oriented tangles, which in the various, you make these representations associated to simple Lie algebras like SLN. But I think, in the case where your simple Lie algebra is the GL1 for the multiplicative group, which sort of falls out, which actually isn't quite precisely part of the usual way these things are presented, gives you a sort of invertible topological field theory for the writhe. I'm trying to say that Brundon has a big list of diagrams that and relations that need to be satisfied. And if you look at the writhe, they're all sort of trivially true. And the writhe is a very special case of his story. And there's a similar story about line bundles on the configuration spaces and their Konechnik-Zamolodchikov connections, which are usually take values in some simple Lie group, not GL1. But you can do it for GL1, and you get something which is maybe a little bit interesting. So the whole point, the kind of point of interest in this maybe is that once you start thinking in this way, there's this interesting subcategory of braids consisting of braids of writhe 0, which are a sort of sub-monoid. And it's no longer braided monoidal, because if you have 2 things of writhe 0 and you cross them, you get an enormous amount of rise from the crossings. So it group completes to some kind of monoid, which you can think of as the motion, which you might try to think of as the motion of some kind of charged particles, which are constrained such that their relative rive always remains zero. And that's some kind of spooky action at a distance, it seems to me. It's a kind of topological interaction, some kind of, quadratic or something interaction between these particles that show up as some kind of higher derived obstructions to things. And it's interesting that these things actually come up quite explicitly in a lot of models in string theory. Before I get too deep into this, before I get too crazy, are there any questions? Let me just say that these groups were first studied way back in the 70s by people in Arnold's school in Moscow, although I think they were not actually students of Arnold. But this was identified back then, but it's I think not very well known, and it took a while for us to learn the literature around this kind of stuff. These derived braids, please excuse, I will draw attention to this silly pun. Define a kind of cover of loops 2 S3. Remember way back here. The hop vibration came up saying that we can think of loops 2 S2 as a bunch of copies of loops 2 S3. But that might not be part of your unconscious thinking unless you were at Bletchley Park or something like that. This kind of thing, so loops 2 S3 is a kind of, you can think of it as a kind of vibration over the circle where this thing is given by the discriminant. The discriminant doesn't actually lift very nicely, but its homotopy class does. And then this is the sort of Milnor fiber for what happens when you go around this circle over here on the right. And so this is double loops on the 3 connected cover of this of the sphere, which is beloved of physicists these days. It happens that every simply connected compact Lie group has a non-trivial third homotopy group, the integers, and it has a canonical 3 connected cover, which comes up for all Lie groups. It's, you don't, here it's in this special case, the SU2 is the simple 3 sphere. In the next step is going to be to construct an invariant for these, the group completion of these, trying to highlight, let me just go away. I'm trying to, I want to describe a very smart construction, which allows us to lift this, construct a map from this, from the group completion of the derived braids to a Picard group of modules over the sphere spectrum that sees some interesting non-trivial higher homotopy. Okay, so to get there, I've inserted a tiny little digression about the group completion theorem, just because the group completion theorem seems to be extremely useful and ought to be better known. So on this page here, I've actually said a bunch of stuff that I've more or less already said. The map induced by group completion on homology is what you get when you invert the elements in pi0 of your original topological monoid. If you're working with a discrete monoid at this stage, maybe you don't get anything. But this does, okay, so also the group completion theorem applied to this guy here gives you Quillen's cohomology, Quillen's algebraic K-theory of rings. And if you apply it to the infinite symmetric product, same theorem gives you the Dole-Tom isomorph. So I just wanted to record this here on this side, this page, to say that if you group complete the braid monoid, you can compute this explicitly, very precisely in terms of Dyer-Lashoff operations. This is essentially polynomial, and it's basically kind of, what do you call it, monogenic, or cyclic on one element over that algebra. So if you're interested in sort of mapping to something, you basically have to control where it maps some kind of a generator. The generator is basically the class in degree 1 given by the map to the circle in that kind of presentation I was just talking about as a sort of Milnor vibration, Milnor-like vibration. Okay, if you don't stop me, I'm going to continue. One of the non-obvious monoids you might think of, if you were smarter than me, is to take an n sphere and smash it with an m sphere to get an n plus m sphere. And that's a preposterous looking topological monoid, which you can group complete. And it turns out that if you do that, what you're looking at eventually is maps from the sphere, stable maps from the sphere to the sphere under composition, as opposed to maps from the sphere to the sphere composed by taking their wedge sum. Okay, that's the usual composition. So one of these is kind of manifestly abelian and the other is not, and they're very different. And if that says that you can think of these Picard groups as classifying spaces for something that you can make sense of as the multiplicative group of the sphere spectrum of homotopy theory. Due to work of many people, in particular Charles Resk, that's going to come up soon, you can do things with this space. Actually, this GL1 thing goes back to work of Madsen and Milgram on the cohomology of BGL under tensor product, at least for spaces over a finite field. I wrote down some technical stuff in the next few pages, which I'm going to sort of try to give relatively short shrift to. One issue is, so I'm going to sort of jump into the p-adic world here, and there's a natural question as to why do we have to, what's the point of doing things p-adically? And there's actually a reference to this a little bit further on. The point being that there's an old theorem of Madsen and Toda that says that if you make a cobordism theory out of spherical vibrations instead of the spherical bundles that you see in classical Tom theory, you get some kind of cobordism theory for something like Poincare spaces or homology manifolds or something like that. And it's actually Eilenberg-MacLane, but it's all torsion. So these questions about, well, Steenrod representability, really, this is a sort of question of, this is, connected to the Hopkins-Mahold theorem, which identifies the Eilenberg-MacLane spectrum, the Eilenberg-MacLane spectrum of the integers as a Tom spectrum associated to loops 2 on S3, or rather, it's infinite cyclic cover. It's infinite cyclic cover. And that's a kind of version of the Steenrod representability theorem, sort of given a kind of an integral homology class, how well can you represent that by something smooth? And the sort of Hopkins-Mahold theorem gives you a sort of canonical way to smooth that cycle p-adically. It's p-adic because the whole problem is torsion, and you might as well localize at some prime and sort of cut to the chase. So anyway, this involves a little bit of p-adic stuff, and it's stuff that Fred Cohen did in the 70s at the prime 2. It's sort of more complicated at odd primes. I mean, it's sort of geometrically more complicated. But so the reason I wrote this out here is to say that the multiplicative group, so the multiplicative group of the integers is plus or minus 1, but the multiplicative group of the p-adic integers is almost the same as the p-adic integers themselves. So it's infinite cyclic, the group of units is. So there is sort of up to some kind of an equivalence, a more or less unique generator of this. But this means that, somehow pi1 of the multiplicative group of the integers is Z2 generated by eta, whereas pi1 of the p-adic integers is the multiplicative group of the p-adic integers, which is more or less a sort of one-dimensional p-adic torus. So it's non-simply connected. It's much more non-simply connected than the p=2 case is, and it passes, and it's useful to pass to the universal cover of this map defined by the writhe. So, if you look at it from the direct computational point of view, it looks like the writhe is in degree 0, and so you have sort of like the number of strands, and then you have the writhe, and then nothing higher. But if you think of it from this point of view, there's some possibly interesting substructure mapped into this group over here, which is rather mysterious. You want to counsel me about the time? How much?
Jack, you've still got plenty of time.
Okay. I don't. Yeah.
But you finish when you want to, really.
Okay, I'd like to, yeah, I would like to get to the preposterous stuff. What I'm trying to say is that we can lift this map from the braid group or its group completion to this Picard group of sphere modules over the sphere spectrum, which has got a lot of homotopy theory in it. But it's a sort of geometric construction. You start with a braid or a diffeomorphism of the plane, and you make this sort of Burau representative of it, which is a big a matrix over some big lambda, this big ring lambda. And what I want to do is make a p-adic sphere out of it by taking the lambda module given by the Burau matrix and sending the parameter t to the generator of this topologically cyclic group. So that takes your Burau matrix and gives you a matrix over the p-adic integers, not such a big thing. And there's this neat construction in sort of algebraic number theory these days, where you take a matrix, take such a matrix, take an element of a finite dimensional Lie, take your finite dimensional Lie algebra, it's useful to think of it as, and define a one-point compactification for it, which is sort of its determinant. And it turns out that this is a thing you can do. And there's some very nice work by Dustin Klaus and Paul Gors. I should say that Agnes Baudry and Vesna Stoyanska are among these collaborators. This is really neat stuff. The reference is in the abstract. Anyway, it says that if you take something like a free group over the integers and think of it as an Eilenberg-MacLane space, take its classifying space, that's a torus. And you want to get from a torus to a sphere. And Clausen proposed this ingenious method of, what do you call it? You basically yank out all the interior entrails and have nothing left but the top dimensional sphere. Evisceration. So you take these toruses and eviscerate them and you get p-adic spheres. There's a sort of formal argument in this for doing this. These things are defined as limits, and you play off limits of Pontryagin duals with limits of Spanier-Whitehead duals. That's sort of what they do. They use Becker-Gottlieb transfers in this paper, of course, and company for this kind of thing. So the upshot is that you get a nice canonical map by this sort of volume of the Burau, or p-adic volume of the Burau representation. And then you fool around with the fact that your Burau, your writhe, is a map of double loop spaces, and thus preserves, and thus commutes with at least the first non-trivial Dyer-Lashoff operation. And that's enough to get you from degree 1 to something like degree 2p minus 3 in the homology groups of these spaces. And this has to do with the fact that the first non-trivial element of order p in the stable homotopy group of spheres is in degree 2p minus 3. So for example, if p equals 2, you get 4 minus 3 equals 1, and there's this element eta of degree 2 in stable homotopy. And then in general, the analog of minus 1, that's an element in K1, for example, of the reals, lives in degree 2p minus 3. And this is actually, spelled out very nicely in an argument of Cohen, May, and Taylor back in the early 80s. So this gives you this construction. This presumably gives you a map to this Picard group. That Picard group is really sort of as inaccessible as the entire homotopy groups of spheres, or maybe more inaccessible. But it has a nice quotient, which is the image of J. Was there a question? Okay, I'm flying blind here. So this gives you a sort of interesting invariant, and that is the variant invariant that you know is non-trivial by the Hopkins-Mahol theorem, by this argument up above. So the Hopkins-Mahol theorem solves, well, does this stuff here. Sorry. This section about this propaganda about E2 ring spectra. The thing is that we already know that the Eilenberg-MacLane spectra have E infinity commutative, and that's as commutative as they may be. But this version is a kind of universal E2 version, and that's of interest to people in algebraic geometry. Because they're all these old unsolved conjectures about products in Hodge theory, whether the Hodge theoretic tensor product is compatible with the standard conjectures, but they're the ones that are still open, I think, if I may have this wrong. Anyway, this group that comes up, this in terms of these strangely interacting derived braids, if you believe in them, look like something considered in string theory called West-Zumino-Witten particles, which those are defined by maps from the two-sphere to SU2. They were originally called sigma models. They're named after the sigma meson, which turns out not to exist. But anyway, this says that smoothings are something like that smoothings of an integral homology class are controlled by something that looks a lot like these fields of particles associated to SU2 that have a long history in string theory. And this just sounds preposterous to me. So I would be very happy if some either physicist or psychiatrist or something would help me. Okay, now let's see if I can get out of here.
Just stop sharing the screen.
Yeah, where is that? Okay.
Should be at the bottom.
Well, they're at the top up here. Oh.
Sometimes it's at the top. It depends. Yeah.
Mhm.
Can I just close that?
Well, that's nice.
There's some lovely young girls
I
there.
don't see you folks at all.
Those are grandkids.
Yeah.
Mhm.
You don't know, Dale, they might be recent. You just have to click on the stop sharing button.
There you go.
Thank you. I'm very sorry.
Okay.
Okay.
Brilliant. Okay, well, thanks very much, Jack.
An honor. Thank you all.
that's a lot of stimulation there. So are there any questions? Does anybody have any?
Yeah.
Dale?
Could you elaborate again why is useful to go into the p-adic integers?
Well, it's just that if you look at a lot of the early literature of kind of algebraic methods, people work over either a field of characteristic 0 or a field of characteristic p, a finite field, because the kind of formula is very nice there, more terms in there. And so you can sort of manipulate tensor product, manipulate products very easily. So what I wanted to say that, so this theorem of Toda and Peterson says that if you try to do some kind of cobordism of homology manifolds, I think there are problems in dimension 4. People like Frank Quinn and others worked around this a lot. But basically, if you're doing homology manifolds or Poincare duality manifold spaces or something like that, cobordism theories or such things, you wind up with an Eilenberg-MacLane space. And Eilenberg-MacLane spaces are well understood, except that these things have torsion of all orders at all primes. So it's basically kind of nasty number theory to work at that level. So one thing you can do is, but the thing is that homotopy theory, sort of higher homotopy theory, falls apart at the different primes. The primes don't interact; they interact very little. It's not like group theory, and so you can work one prime at a time. And so it actually, this stuff about p-adic methods is now kind of well developed. And so if you can control things at the point P over a finite field, then nowadays it's not so hard to just lift the whole contraption to the p-adic numbers. And then you get something that has a characteristic 0 equalization so that you can compare them at different primes. That's sort of what Dennis Sullivan wrote up in one of his annals papers, or maybe his annals paper. And the thing is that p-adic numbers, I mean, they're topological fields, and the topology is actually a lot easier than in the classical cases. If you can sort of make sense of something, of an infinite construction, then it converges. Under normal circumstances. So it's actually not that hard to work with. I don't know if that, it's, there's this thing by Tokuyushi Kato, the number theorist, that the sun is very bright and it kind of blinds you in the daytime, but then at night the stars come out. And so this is like the Archimedean primes are very bright, but sometimes they go away, and all you have to do, and you have this infinite number of primes to work with that you have to contend with. That's a slogan. That's not an answer, I guess.
That's very philosophical.
Yeah.
Does that answer your question, Dale?
More or less.
Section. Anyway, if I could say something, these series of talks, which I think have been a success, I would, and we, sometimes we have talks such as Jack's on the cutting edge of things, which are, the very cutting edge. And I would like, of course, to continue this, but also to kind of shuffle them with some talks which explain aspects of mathematics, to say kind of like MSc level. So I invite anybody to give a talk on something which perhaps they know about and maybe other people may or may not know about. For instance, I could call on Colin to give a talk on block bundles. Maybe somebody could give a talk on K theory or the Picard group, even. You know, so there's something to think about. Anyway, thanks again, Jack, for your talk, and it was very interesting. Next week, yeah. Next week, Scott, I think, is going to talk the usual date and time. Is that correct, Scott?
That's correct. And I'm hoping that it will be elementary, but
yeah.
What I consider elementary is something that I know.
Well, that's always the problem.
So are we back to Tuesday?
Yes, we're back to Tuesday. This was just a blip. Yeah, I went to Ronnie Scott's jazz club, so that's why I wasn't here.
Who played?
Well, actually, it was my son, so I had.
Oh, wow!
Was it just him or in a group?
No, he's in a group called the Filthy Six.
The Filthy what?
Six.
Filthy Six.
Yeah.
How many people are in the group?
Nice bunch of guys. Anyway, you can check them out on what is it? Spotify.
YouTube.
Okay, so I better stop now. And we look forward to hearing Scott next week. So one more time, thank you, Jack, and see you next week.